Hello and good afternoon. So, um, an update on the method of delivery for the lectures. So far, the university has given me an exception to continue teaching remotely until the reading week. What will happen after the reading week is not yet finalized. So as soon as that gets finalized, I'll let the class know. For the labs, lab 1 demos will be, at least at this point, they're scheduled to be remote. If that changes, I'll, I mean, for the demos, just wait for the email to be sent to the class, but with high probability, the demos will be online and remote. But lab 2, you will have to come to the labs. So that's pretty much where we are. Now, again, for labs, just wait for an email. But what I can say with regard to the lectures is that we're going to continue remotely until the reading week. And that's fixed and decided. So I'll send an email to the entire class on that topic. Okay, so let's continue where we left off in the last lecture. So we're talking about uniprocessor scheduling, and we talked about the metrics that we are interested in. And the first scheduling policy that we're going to see is called first come, first serve. As the name suggests, this means that whoever comes to the ready queue first, they're going to be the one who is going to be scheduled first. Now, if a thread goes for I/O for an I/O burst and then comes back, then it goes to the back of the to the back of the queue, and basically every time a thread is suspended and comes back, it will be added to the end of the queue. And the scheduler always picks threads from the head of the queue. Now, here is an example. Let's say we have T1, T2, and T3, and let's assume that they arrive in the order of T1 comes first, T2 comes next, and then T3. And let's assume that T1 has a CPU burst of 24 units of time. For the sake of argument, let's say microseconds here. It could be anything. Let's say 24 microseconds for T1. T2 has a CPU burst of 3 microseconds, and T3 has a CPU burst of 3 microseconds. Now, the way FCFS works, obviously, we're going to first run T1 for 24 microseconds, and then we'll context switch to T2, and once T2 is done, we context switch back to T3, and we're done. So now this here right here is a workload. If I'm to remind you of the terms that we talked last time, so a workload is a set of tasks or threads that we'll consider. So for this particular workload, this is how FCFS works. Now, let's look at those metrics that we introduced in the previous lecture, and let's examine them. So what is the wait time for T1? Wait time for T1 is 0. T1 did not wait. Let's assume that T1, T2, and T3 all came at T0. But T1 was ordered first, and then T2, and then T3. Now, the waiting time for T2 is 24 microseconds, 24 units of time, whatever that is. And for T3, it has to wait for 27 units of time until it gets to execute. So wait time is just from when the task came until it started running. Now, average wait time in the system, averaging over all tasks, is 0 plus 27 plus 24 plus 27 divided by 3, which is 17. And average response time. Now, what is response time? If you remember, response time is the time from when the task comes until it finishes. So response time of T1 is 24, response time of T2 is 27, and response time of T3 is 30. Now, if you get average of this, it's going to be 27. What happens if we change the order? Let's now this time assume that T2 and T3 came first or were ordered first, and then T1. Then the scheduling will change, obviously. But let's look at, so in this case, well, first come, first serve, 2 runs, 2 3 runs, and then T1. Let's look at the same metrics again. So what is the wait time? Wait time this time for T1 is 6, right? So T time started at time 6. So it waited for 6 time units. T2 did not wait at all. T3 waited for 3. Now, average wait time is 3. So average wait time decreased substantially. What about response time? Well, it equally decreased substantially as well. So the average wait time decreased from 17 to 3, and average response time decreased from 27 to 13. So this second scheduling was a lot better with respect to those metrics than the first one. Now, this should give you an idea that how FCFS performs depends on when tasks come. So it's very, it varies, right? It depends on who comes first. In some cases, it could lead to really good outcomes like this one. And in some cases, it could lead to really bad outcomes like the first one. In particular, it's kind of like it depends on this big task. If this big task comes first, then everybody has to wait for it. Whereas if the short tasks come first, then they can get out pretty fast, and then the long task starts running. Now, the strength of FCFS is it's simple. Implementing it is pretty straightforward. The downside is that it allows short tasks to get stuck behind long tasks. And as such, the response time of the system is highly variable and could be actually suboptimal. And this is just an example showing what happens with FCFS in a system. So here I have arrivals for these short tasks. Now assume that, so what do we have here? So above the line, I have the task that is running. Below the line, I have the arrivals. And the length of each one of these bars indicates the length of each task, the CPU burst of each task. And the order in the vertical axis is the order of these tasks in the ready queue. Now, once I'm done with the purple task, I start the blue task. And after that, I start the green task. Let's say another task comes. It goes to the top of the queue. Let's say this task that arrived was a long task. So what happens is what you're seeing. So I'm going to spend a lot of time running this red task. And while I'm running that task, new tasks can come, and they get queued in the queue. So I end up with this like a really bad situation in my ready queue because I had this really long task. I get backlogged in my queue, in my ready queue. Now, the second scheduling policy that we're going to look at is called round robin. So FCFS was kind of like bad because it was sacrificing these short tasks for that big task that arrived at the beginning. Now, one way we can deal with this is to divide time into time quanta of, let's say, similar sizes. So a unit of time, we call it a time quantum. And we kind of give time quantum, one time quantum to each task. And then we preempt that task and give the CPU to the next task in the queue for that same amount of time. And then repeat this. We go to the next task, we go to the next task, and so on and so forth. And what we are going to do, once a task gets CPU, we're going to put it at the end of the queue. So we just look at the head of the queue. We give whatever task is at the head of the queue to run on the CPU for a given time quantum. Then we preempt that task. We context switch to the next task on the queue, and we put the currently running task back to the end of the queue. So this is called round robin. Obviously, it's not this guy. This fluffy round robin is not what we mean, although this is absolutely cute. So let's put a heart here. So now you might ask, okay, what should be this time quantum? What should be the size of this time quantum? It depends. Like you can choose what time quantum size makes sense for your system. As we will see in modern operating systems, we don't have fixed time quantum, so it's variable. It changes the length of it, but we'll talk about that later. But it depends. So you can pick any time quantum you wish, depending on on what kind of tasks you're running. Now, depending on the length of your time quantum, you might actually see different behavior from your system. So we're going to talk about how the length of time quantum affect the metrics that we're interested in. For example, the waiting time, the wait time, the response time, and all of that. Now, one of the benefits of having round robin a scheduling policy is that whatever that length is, let's assume the length is Q, and let's assume that you have n tasks in your system. We are sure that each task gets to run for Q amount of time every n times Q time period. So for a period of n times Q, my task is going to run at least for Q, right? That's the beauty of round robin, because everybody is going to get Q, and then we're going to go back to the first one. So in a, if there are n tasks in the queue, so n times Q is length of the time quantum, my task is going to run somewhere here for Q amount of time. So it's kind of like I'm making progress for a queue every NQ time period. Now let's look at an example. So let's say we have 4 tasks, and you can see the bursts, CPU bursts of each. So basically T3 is the longest task, T1 is next, T4, and then the shortest task is T2. In this example, I assume that the time quantum is 20. So let's assume that whatever time unit the CPU burst is, the same I'm using for time quantum, 20, let's say 20 microsecond. And let's say the order in my queue is basically T1, T2, T3, and T4. So I give 20 time quantum on CPU for T1. Then I switch to T2. Now T2 doesn't need 20 because its CPU burst is only 8. So it finishes after 8. So from 20 to 28, T2 finishes. Now I switch to T3. I run for 20. Then T3 is put at the back of the list. We go to T4. T4 runs for 20. Go back to T1. Now this time I go to T3 and then T4. T4 already has finished 20, so there's only 4 left. So from 108 to 112, I'm done with T4, and then the rest of it I switch between T1 and T3, which makes sense. These two were the longest ones. So at some point everybody else is done. Now I'm just going back and forth between T1 and T3 until these guys are done. Obviously T1 is going to be done first, and then at some point I only have T3, so I just give the CPU to T3 until it finishes. Now let's look at all those metrics that we were interested in this context. So what is the wait time of T1? How much time T1 waited in this case? So this is the first time T1 was scheduled and it didn't wait anything, so 0. The second time T1 was scheduled, it's here. How much did it wait? It waited from 20 to 68. So that's here, 68 minus 20. Next time T1 was scheduled is here. So how much did it wait? It waited from 88 to 112. So 112 minus 88. So in total, T1 waited for 72 time units. The same you can calculate for T2, T3, and T4. And if you do that and then average over 4 tasks, this is going to be your average wait time. Now, this calculation is a little bit easier for response time. For response time, all you need to do is basically, let me clean this up. So for response time, all you can do is you can just look at when each task is finished. So T1 is finished here, so its response time is 125. That's what you see here. T2 finished here, so its response time is 28. T3 finished at the end, so 153, and T4 finished here. Although I have to say this works because all of them were assuming that all of them were in the system at time T0. So if a task comes later on, then you should look at when it finished minus when it arrived at the system. So that duration becomes the response time. But in this particular example, because all of them were in the system, so we can just you can just look at when they finished, because when they came to the system, the time was 0. So finish minus 0 is just finish. Okay, so let me see. There is a question. So in round robin scheduling, even if a task finishes earlier, the scheduler just leaves the CPU idle until the end. We reach the end of the time quantum. Why wouldn't the scheduler start another? Oh no, as you can see, I mean, it's probably because of this figure, you think that all these time quanta are the same, but look at these numbers. So it's from 20 to 28. I didn't wait for 20 time quantum. I just, once T2 was finished, I started T3. So yeah, you don't need to wait until the time quanta. The time quantum is done. You can, once T2 is done, you can immediately context switch to the next task. Yeah, I think the probably the question has arisen because visually these boxes are the same size, but look at the numbers. So my fault. I should have made them different sizes, but hopefully my explanation makes it clear that, yeah, we don't wait. Okay, now let's have some discussions about round robin. What is the benefit of it? The benefit is that it's this time it's better for short tasks because they're not going to wait for the long tasks, right? They're going to just end soon. What is the downside of round robin? It requires a lot of context switching, as you just saw here. Like if we were to run this with first come first serve, we would run so it would be like we run T1 and then we run T2 and then we run T3 and then we run T4. So only 1, 2, 3 context switches, right? We would just do 3 context switches and we're done. With round robin, we're doing 1, 2, 3, 4, 5, 6, 7, 8. We are doing 8 context switches. So 3 context switches compared to 8, right? And this is just for time quantum 20. If let's say time quantum was 10, maybe we would end up doing a lot more context switches. So now context switching has overhead, as we saw when we were implementing in the previous lectures where we talked about context switching. It has overhead, right? And if you're doing it a lot, you're paying that overhead. And this overhead shows itself when you're calculating throughput. Now, in the previous slide, I assume that there is 0 overhead, which is kind of like, you know, ideal. So if the context switching overhead is 0, this is what you're going to see, right? Immediately after T1 is done, I can just start T2. And usually that's the case, right? In the exams, we specify that consider, you know, context switching overhead to be 0. That makes it easier to analyze. But in reality, context switch has cost and it's not 0. So let's say if T1 ends at 20, then we're going to pay like some, you know, 2, 3, let's say nanoseconds or microsecond, whatever cost for context switching, and then start T2. And this time that we're spending on context switching, we're not spending on running the tasks. So here, for example, in first come first serve, we're paying this cost. Let's say this is the time that we're going to spend on context switching. We're going to pay this cost 3 times. Whereas in this case, we're going to pay this cost 8 times. And while we're context switching, we're not running tasks. So this is going to impact our throughput, because at the end of the day, in both of these 2 cases, I'm running 4 tasks. So here I have, I'm running 4 tasks in a shorter amount of time than here, because here I'm paying 8 times the overhead. So the duration that it takes me to finish all of them is going to be more than if I were to run FCFS. So I finished 4 tasks in FCFS in a shorter amount of time. So then the throughput is higher, right? So that's the downside of round robin. Now, the other thing to note about round robin is that the behavior changes as you change the length of your time quanta. So the length of the time quantum is important in what kind of outcome you get. For example, what happens if this time quantum that you have is very, very long? So if it is very, very long, then your response time suffers, right? Because it takes more time. If you remember, we were talking about that. You know, if there are n tasks in the queue, the response time for the wait time for the last one is nq, or n-1 times q, because it has to wait for all the n-1 tasks before it to get their time quantum until we come to this one. So if wait time goes up, then the response time goes up as well. So if you're going to wait more because the time quantum is longer, therefore your response time would also suffer. Now, if it is too slow, or sorry, if the time quantum size is too short, then we're going to have a lot of context switching, right? We're going to context switch a lot more compared to long ones. And as I mentioned, more context switch, more context switches means more cost for throughput, exactly. So throughput will suffer. You're going to finish the same amount of job in a longer period of time because you're paying this context switching cost more. Now, for example, if the size of time quantum is infinite, so basically I give the CPU to you for infinite amount of time until you finish, well, what happens is that you're basically reverting to FCFS, right? So this makes round robin to become like FCFS, because every task that is the head of the queue will run until they finish their CPU burst, and then we go to the next task. So it's kind of like first come, first serve. Now, the rule of thumb is if this is the length of your time quantum, then after this, you're going to pay this context switching cost. So this is context switching cost. Now, if this guy is Q and this guy is C, the rule of thumb is C divided by Q plus C should be about 10%, less than 10%, 5%, right? So you want the cost to be negligible compared to the whole duration, right? So usually it's, you know, they first measure the cost of context switching, and then they set the time quantum so that the cost is negligible compared to how long a task is going to run. Okay, so now we can ask this question, okay, we know that the time quantum is important. Is there any relationship between the size of the time quantum and these metrics that we're interested in? Can we say, for example, if time quantum increases or decreases, can we say if average response time increases or decreases? Is there any relationship, direct relationship between the two? And the answer to this question is unfortunately not. So let's look at an example. So here I have two tasks. So my workload consists of two tasks, T1 and T2. T1's burst is 10, T2's burst is 1. Now, let's run this workload for round robin with different time quantum sizes. Let's just start with time quantum equal 10. So Q equals 10. Now, in this case, it's kind of like first come, first serve. So we're going to give 10 time units to T1. So T1 ends, and then we context switch to T2 and finish T2. Assuming that the context switching overhead is 0, now average response time is T1 response time is 10, T2's response time is 11, so average is 10.5. Now let's decrease the time quantum to 5. So I decrease the time quantum. Now T1 runs for 5, T2 runs to finish, and then T3, and then we go back to T1. Now the response time for T1 is 11, for T2 is 6. And the average response time has gone down. So I decrease the size or the length of time quantum, and my average response time shrinked. So this is one example. Now let's look at another example. So let's say that I have another workload, T1 and T2. T1's CPU burst is 1, T2's CPU burst is 1, and time quantum is 10. Now T1 runs for 1 time unit and then finishes, and then we go to T2. So the average response time is 1.5. Now if I decrease Q to 1 or to 5, doesn't matter, nothing is going to change, right? We're going to still run T1 to completion and then switch to T2. So response time does not change. So in this case, I decreased the length of the time quantum, but my average response time did not change. Now let's see another example where the average response time actually increases. Here I have the previous workload, 1 and 1. Let's do Q equals 1, which is what we saw with response time of 1.5. Now let's decrease this to 0.5. So let's assume that time quantum is 0.5. Now, as you can see, T1 finishes at 1.5, T2 finishes at 2, and the average is 1.75. So response time has increased by decreasing the length of the time quantum. So the merit of this, the takeaway is that there is no direct relationship between the size of time quantum or the length of the time quantum and the average response time. Okay. So yeah, so this is a little bit of history. So when, like in early Unix systems, the size of time quantum, the length of time quantum was like about 1 second, and it worked because the system didn't have many users and users didn't have many processes. So it's fine for those limited cases, but as you get, to have more users, or as your users get to have more processes, then you can see that, if you want to click on your screen and you have to, you have 10 other processes in your system, it might take 10 seconds for your mouse movement to show on the screen, right? You make a move, but it takes like, like if whatever number of processes you're running times 10, let's say you're the last one to see that on your screen, and that's absolutely not responsive at all. So that's that. These are typical numbers, and I have to say, even this has its own, take it with a grain of salt. These numbers are usually for general purpose systems. Like if you're talking about, servers at Google or Amazon, they work with a lot less context switching time. So yeah, and as we'll see, more advanced scheduling policies change the length of time quantum dynamically, depending on how many tasks there are in the system. Okay, in my slides, I have a different thing that I said to you. I said one. I think in previous slides I said 10%. In my slides I have 1%. But anyhow, like you can set that given what is reasonable to your system. If 10% is reasonable, if 5% is reasonable, if 1% is reasonable, you can just measure. So the idea is to measure how long it takes for your context switching, and then given that, set the length of your time quantum to be whatever percentage is that makes sense in your system. 1%, 5%, 10%, whatever. Now let's compare FCFS and RoundRobin. If there is a zero cost for context switching, then RoundRobin, can we say RoundRobin is always better than FCFS? So let's assume that there is zero context switching cost. Can we make this assertion that RoundRobin is always better than FCFS? Now, whenever you see a question like this, with a term like this, better, you have to ask with what, what is the metric that we're looking at. And if the metric that we're looking at is response time, the answer could be different than if the metric that you want to compare the two is fairness, for example. One thing that you can say is probably RoundRobin is more fair than FCFS. But when it comes to performance, then it really is not a clear cut. Let's look at this example. So let's suppose that I have 10 tasks, and each task is going to take 100 seconds. And let's say that the time quantum is 1 second. The length of time quantum is 1 second. Now, with FCFS, T1 is going to finish after 100 seconds, then T2, and all the way to T10. With RoundRobin, we're going to context switch every 1 second, because that's the length of our time quantum. Now, both of these two systems, if the context switching overhead is 0, then both of these two systems finish tasks, all of them, at the same time, right? Both of them will finish running all the workload at time 1000. However, if you look at the response time of FCFS compared to RoundRobin, in RoundRobin, tasks start finishing at 991, right? So whereas in FCFS, the first task actually finishes at time 10, time 100. So overall, the response time of RR is a lot more than the response time of FCFS, because almost all of these numbers, all of these numbers are like this, right? So all of the completion times in RoundRobin are greater than the completion time for the same task in RR. So the response time of RR is much worse than FCFS. However, if you look at fairness, you can see that, well, it's kind of fair. Like the response times are close to each other, right? Whereas here, one task finishes at time 100 and another task finishes at time 1000. So it's kind of like we're not fair to this last task. We're keeping it all the way to the end, and we kind of give this task a go at the beginning. So FCFS is kind of not fair, whereas RoundRobin treats everybody fairly. So all of them are like kind of close to each other, they finish, right? So, okay, so we can't make this assertion that one is better than the other one, right? The other thing to consider is with FCFS, the response time depends on the order of tasks. So one scenario could give us a really good response time, and another scenario could give us a really bad one. Okay. Yeah, so in this particular scenario, the response time, average response time in RR is really bad. If in real systems, the context switching overhead for RR is going to be huge, right? Which would then make your throughput suffer in RR greatly compared to FCFS. And this again would depend. So for FCFS, the scheduling depends on the order at which tasks come to the system. And in round robin, as we saw, the behavior of the system depends on the length of the time quantum. So let's say, going back to that example of 4 tasks where T1 and T3 were the longest tasks. So if you remember, I had 4 tasks, 2 of them were long and 2 of them were relatively short. So this is the best FCFS execution time in terms of response time. So the best scenario for FCFS is if the shorter tasks come first and the longer tasks come at the end. So this gives the best response time. So we can just put these numbers here. So for wait, like in this table, I have wait time and response time. So here are these numbers for best FCFS. Now you can now do worst FCFS, which happens when the longest task comes first and the shortest task comes the last. So this gives you the worst case response time. So then we have these numbers, as you can see. So the best case is 31 1/4, whereas the worst case is 83 1/2 in wait time and response time. Now let's look at round robin with different time quanta. So in this particular example, we're looking at this one where the length of the time quantum is 8. So this is how it's going to look. So you can convince you can trust me that these are the numbers, or you can calculate them by yourself. Now let's do that for different time quanta. So I have populated this for you. Now let's stare at this table a little bit and look at the numbers that we're seeing. Now, one thing that I want you to note is this one. So these numbers are quite the same across the board, right? So for T3, I'm kind of getting the same numbers regardless of the size of time quanta, the size of the time quantum. And for T2, these numbers are really different. So what's going on here? So why is it the case that for 3, these numbers are quite the same? And the answer is, if you remember, T3 is the longest task. So for the longest task, it really doesn't matter what the size of your time quantum is, because it's going to finish at the end. It's not going to, like, either in best case FCFS or any of the other round robin schedulings with different time quanta, the longest task is going to finish the last. So it's going to end at the end. And note that this is just true if the context switching overhead is 0. If context switching overhead is different, then that's not going to be true, right? Because the shorter your time quanta, your time quanta are, the later you're going to finish your last task. So these numbers would change if you have context switching overhead considered. Okay, so we're done with the first two. So we talked about first come, first serve. We talked about round robin. The third scheduling policy that we want to talk about is shortest task first. As the name suggests, in shortest task first, we're going to just run the shortest task first. We finish it, then we move on to the next one, and then we move on to the next one, and so on and so forth. Now, this mirrors the best FCFS scenario that we saw in the previous slide, right? So basically, you can prove that shortest task first is basically the best optimal FCFS order, where the arrival of tasks are based on their execution time or their CPU burst. So the shortest came first, and then the longest came the last, and that gives you the best response time. Another phrase that is used for shortest task first is shortest time to completion first. So this one is for scenarios where you don't have preemption. So basically, you just, every time you pick a task, you pick that task to be the shortest and you finish it. And then once it's done, you look at all the tasks that you have, and then you pick the shortest among those. Now, if you add preemption, it's going to change to shortest remaining time first. So every time that you want to make a scheduling decision, you look at how much time is remaining for each one of your tasks, and you pick the one that has the shortest amount of remaining time. Now, at some point, a new task comes and preempts the current task. Now you can make a decision again. So you can look at how long you have left for this task that you were running, and you can compare that with the new task that has come, and see if the new task is shorter, then you start the new task at this point. So if you have preemption, then the equivalent of shortest task first is shortest remaining time first. So at any point, we just look at the remaining time of each task. Now, somebody's asking, how does the scheduler know the duration that each task will take? Great question. The scheduler doesn't know. So this brings us to the so first of all, I'll answer that question. So it doesn't. So that's the downside of SGF. We'll talk about it. So we talked about the idea. The idea is to get rid of the short tasks first. This improves our response time. Now, you can prove that this leads to optimal policy. So if you only care about response time, so if you care about like being super responsive and you want to optimize this metric, you want to get the best response time possible, the optimal scheduling policy is SGF in non-preemptive settings and SRTF in preemptive settings. And you can prove that. I'm not going to prove it. This kind of like is a very short proof. You can read it and convince yourself that it works. So you can prove that SGF and SRTF are optimal. So that's that. But now let's talk about the question that somebody asked. Although this improves, this minimizes the average response time. Yeah, okay, so let's see. Yeah, so although it minimizes the average response time, but the fact of the matter is that in real systems, we don't know how long a task takes. So it's kind of like impractical. So that's the downside. So the strength is that it's the best when it comes to average response time. The downside is that it's completely useless because it's impractical to implement such scheduling, because we never know how much time is remaining of each task, unless, like, you know, in some very specific settings where everything is deterministic and you have a set of deterministic tasks and you know exactly how each one of them run and there is no randomness in your system, which none of the real systems that I know of are deterministic. So in essence, this is absolutely impractical. Now let's compare SGF or SRTF with FCFS. Well, obviously, it's optimal. One of them is optimal. The other one depends on the order. But under what scenarios are these two the same? Well, if the length of all tasks are the same, then FCFS is equal to SRTF. Both of them work equally, right? If tasks have varying sizes, so they're not equal in size, then obviously SRTF is going to be the best in terms of response time. However, yeah, so that's that. Yeah, so there's no however. So there are scenarios where FCFS is the same as SGF, and that scenario is when all the tasks are of equal size. Okay, now let's look at an example to compare FCFS and RoundRobin and SRTF. So we're putting all three of these scheduling policies and we want to compare them. So let's assume that we have A and B. So these two tasks are really long. Let's say they take a couple of days to finish, or they take a week to finish. But task C is kind of like, it does a CPU burst of 1 millisecond, and then it does a I/O burst of 9 milliseconds, and this continues, right? So these are the two. These are the three tasks in my workload. Now let's see how FCFS, RoundRobin, and SRTF do with this particular workload. Now, if you run A and B by themselves, so if you just have A or if you just have B, they're going to run on your CPU. They're not ever going to go to I/O according to these assumptions. They don't have any I/O. So your CPU utilization is going to be 100% for those tasks, because they're going to just run forever for a week. So you will get a really good high CPU utilization. Your I/O utilization is going to be 0 because they don't have any I/O. If you just run C, if you didn't have A and B and you were just running C, then your CPU utilization is 10%, because every 10 microsecond, you're only using the CPU for 1 microsecond. So you get CPU utilization of 10% and I/O utilization of 90%. So this is just, looking at these tasks individually. What happens under FCFS? Well, it depends on which task you start first. If you're going to start with A and B, each one of them, if they come first, then C is going to just starve almost, right? So the response time of, let's say the order is A, then B, then C, then A is going to wait for 0, but then B is going to wait for 1 week, and then C is going to wait for 2 weeks. So really poor average response time. What if you do round robin or SRTF? So let's look at that. So first, I'm going to do round robin with a time quantum of 40 microsecond or millisecond. Sorry. So let's just start with C this time, just for the sake of argument. I'm going to run C, and C is going to just run for 1 microsecond. So it will then give away the CPU and starts doing the I/O. While it's doing I/O, I context switch to A, and I run A for 40 microsecond, and then I context switch to B. Now, at the end of this I/O here, C comes back. So C goes at the end of the list. So now we go back to C. C does a 1 microsecond again, 1 millisecond, and then goes for I/O. We go to A, B, and this continues, right? So this is one example. Now, if you look at this, we can look at CPU utilization is 100%. So we are always using the CPU. It's work conserving. So CPU is fully utilized. If I look at I/O, however, I/O utilization is about 11%. So if you do the math, you know, this is 40, this is 40, this is 1, and this is 9. So it's 9 divided by 81. So that's about 11%. Now, let's look at round robin with 1 millisecond time quantum. So these systems are assumed to not be looking at task priority for the analysis, right? Yes, at this point we don't have any, like, the priority. It's actually not the case. So you always have priority, right? It's just how you define priority. So in FCFS, your priority is your arrival time. So if you arrive earlier, you have higher priority. In SGF or SRTF, your priority is how long your task is, how much remaining work do you have, and that would be your priority. The less amount of work you have, the higher your priority is. In round robin, everybody has equal priority. I kind of scratched myself. God damn. Okay, so doesn't bleed. Now, if you're talking about priorities in the context of exogenous priorities that, you know, we give tasks, we say this task is high priority, that's that task. Yes, these ones have their own notion of priority. So they define their own priority, and based on that, they schedule. So they kind of disregard whatever priority a user has in their minds about these tasks. FCFS defines its own priority, basically based on the arrival time, and so on and so forth. Now, next we will talk about priorities that are specified by users, and we discuss how that could change the scheduling policy. So that comes next. Okay, so here is if you look at this with 1 millisecond, this is going to be how it's going to look like, and this will give you a really better CPU utilization. Now, just to look at this one microsecond, so we're going to run C, and then C is going to go for I/O. So while C is not there, we're going to do A, B, A, B, A, B, A, B until C finishes and C comes, then we can schedule C. And if you do SRTF, it's going to be, you know, you do C and then you go to A, and then every time C comes back, it gets to run immediately. Compare that to this case here. When C comes, it will go to the end of the list and then waits for its turn to come. In SRTF, every time C comes back from I/O, it immediately gets the CPU because it's the shortest task. It runs and it goes for I/O, and you keep doing A until A is done, and then you will go to B. So this gives you the best I/O utilization of 90%. Now, I guess let's talk about the problems with SRTF. The first one is a starvation. Now, if you are a long task, as you can see here, for example, B is not going to get CPU at all until A is done, and then we go to B. So if you have really long tasks, they can suffer. So because they're going to be the short tasks are going to be prioritized. So long tasks will starve. The overhead is high, right? Because you might end up preempting the ongoing task so many times. Again, like this example, you keep preempting A every time C comes. So a lot of preemption. And it could be unfair, right? These two are very related, starvation and unfairness. So you're kind of like unfair to large tasks. But the most, the strongest downside or the most serious downside of SRTF is the fact that it's impractical and it cannot be used in real systems because we usually don't know how long each task takes. Now, you might attempt to predict how long your tasks take, and that could be used as a heuristic. And one way to do this is to keep a moving average for each task, and every time you run your task, you measure its CPU burst until it asks for I/O, and then you kind of average how long it took on average for this particular task to run. So after a while of running a bunch of tasks, you might get a good sense of if there is any regularity in your tasks, you can discover them, right? You can say, okay, this task has a loop, and in this loop, it spends this much time on CPU and then goes for I/O, right? For example, in that example that we had A, B, and C, let's say initially we didn't know how long for C it takes to use the CPU. What's the CPU burst of C? We could just experiment. We can just give CPU to C and observe that it finishes after 1 microsecond, and then learn that, right? We can have some notion of learning. This is a very simple learning algorithm, right? So this says that you can just, approximate the duration of your CPU burst by some function approximation, given the previous data that you have. This is where it connects to machine learning, sort of, right? So you have some experiments in the past about how long it took for your task to run, and you can just approximate based on that. And this is the most simple and widely used approximation in systems, which is kind of like an exponential averaging. It's a moving average. So let's say, depending on this alpha, you weight your previous experiment and your previous estimate, right? So if alpha is very close to 1, let's say if alpha is 1, then your prediction is always whatever it was last time. So if last time it took 10, you're going to say this time is going to take 10, right? So you kind of like forget about past. You just look at forget about long-term past. You just have a short-term memory about what happened last time. If alpha is close to 0, then you put more weight on on long-term memory. So you kind of like remember past for more. This also is widely used in optimization theory. So we actually used something like this for a system that we designed. So if you look at, for those of you who are interested in reinforcement learning or optimization theory, like the Adam optimization looks at the gradients. So you want to do gradient descent on your objective function in your, let's say, deep learning. So you measure this gradients and you want to move towards this gradient. So with vanilla gradient descent, you basically move in the direction of your gradient and you move as much as the gradient is. Now, one way to do this in better way to avoid like fluctuating is to have a moving average of your gradients. So instead of moving in the direction of your gradient with the size of your gradient, you move in the direction of the moving average of gradients. So you remember what the average gradient was and you move to that direction. So let's say if you're, instead of moving like this towards your goal, so this was 1, this is 1, then you move towards the average. So this becomes your moves. Instead of fluctuating up and down, you go smoothly towards your goal. So this is very famous, this moving average. It's also used in TCP protocol to, if I'm not mistaken, to calculate the, I think it's used for congestion control in TCP. TCP protocol, congestion control, has this exponential moving average. Yeah, very simple but widely used technique. Okay, so I guess I'm gonna kind of jump, or maybe I mentioned this for when we start talking about Linux. Now, if you're gonna do any sort of prediction about your tasks, be advised that at the end of the day, these are predictions and they're approximations. Now, it could well be that you might be able to get a good approximation of the CPU bursts of your application. Now, how do you want to use this information is important. So, in some Linux schedulers, as we will see later on, I have a slide on that, people started guessing what kind of application it is based on its CPU burst time. And that led to a disastrous scheduling policy, which was removed from Linux kernel very fast. So people started doing these approximations based on the measured CPU burst time of tasks, and then made some inferences based on how long this task runs. For example, if they would see these short burst times, they would assume that this is some kind of interactive application. For example, maybe it's kind of like the user is interacting with this thread. So during the interaction, there is a burst, and then it goes to sleep, and then comes back, another burst. So it's an interactive application. And if it is an interactive application, I probably want to prioritize it so that it gets more CPU time. It gets more priority. So I bring down the response time, and I give my users a better experience. So if you can detect that a certain application is an interactive application, meaning that it's interacting with the user, And if you care about users' experience, you might want to prioritize this task. Then people thought that this is good. So I can just measure these bursts. And if I find these really short bursts, I can assume that this application is an interactive application, and I can give it a really high priority. But it turned out that sometimes some other applications might also have short CPU bursts, or maybe some interactive applications might have long CPU bursts. So what happened in Linux kernel scheduler specifically was that some actual interactive applications ended up being classified as non-interactive, and their priority went down, and some non-interactive applications got classified as interactive, so they got higher priority, and overall user experience degraded because the system was making wrong classifications based on wrong assumptions, and then was scheduling the tasks based on those assumptions, and that all led to really bad user experience. So be careful at the end of the day if you're doing these predictions and if you're inferring anything about the type of your application. You know, it's not always accurate, and it could actually lead to bad outcomes. Yeah, so the name of that scheduler was O1 scheduler that was making these assumptions. So I have a slide at the end of this lecture talking about Linux scheduler, the history of Linux scheduler. So when we get there, I remind you of this. Okay, so the bottom line with SRTF is that it's not practical. So you might ask, okay, if it is not practical, why did we even study it? The reason is that it's optimal, right? So we can use it as a benchmark. We can compare other scheduling policies with this one, and we can say if they're doing better or worse than they can't do better because it's optimal, but we can say how close a particular scheduling policy gets to SRTF, for example. So we can use it as a benchmark. So it's optimal, it's hard to predict the future, too much context switching, and it's unfair. So that's basically the summary. Now let's talk about priority. So somebody asked about priorities and whether or not these three algorithms disregard them. And yes, they do. So now if you have priorities exogenous, like users are putting priorities on tasks, which is going to be the case in your in lab 2. So we're going to have tasks, and tasks are going to have priorities. One is scheduling. So this is the fourth scheduling policy we're going to see. It's called strict priority scheduling. Now with this one, you have predefined priorities. In this case, priority 0 to 3, for example, or a system could have different numbers of priority. And with this strict scheduling policy, we order tasks. So we put all the tasks with the same priority in the same priority queue. And as long as we have tasks in higher priorities, we run them first. So we're not going to ever come to lower priorities, depending on which one is lower. Like if priority 0 is the highest priority, then you start with this queue first. If this is your highest priority, you start with priority 3. So it doesn't really, like, I'm not making numbers to mean anything here, but you start with the highest priority queue. So you run those tasks, and then you come to the next ones. Now, how do you schedule between tasks with the same priority? You could do anything, right? You could do FCFS within the same priority. You could do round robin. It doesn't really matter. So you basically run those. Once they're done, then you go to the next queue. And once that queue is done, you go to the next one, and so on and so forth until you finish. So what's the problem with this? So the problem is a starvation, obviously. So you could end up starving the tasks with low priority because you're never going to go to them. And unfortunately, I again have priority inversion here without defining it correctly. But as you can see, there is more on this later. So I'm going to again postpone this. So this actually could suffer from priority inversion, especially when you add synchronization to this. So, if you have cases where a high priority task needs to lock the same mutex that is locked by a low priority task, then your high priority task could get blocked, right? Let's say this task 3 wants to lock a mutex that is already locked by task 6, which is low priority. So this guy gets suspended. Now, this is not called priority inversion. This is just reality of the world. You want your critical section to have mutual exclusion. Now, priority inversion comes when a task 4 comes, which has a lower priority than task 3, but a higher priority of task 6. Now, when T4 comes, obviously T4 will run, right? So we end up making T3 wait for T6, who is now waiting for T4. Now, in reality, we should have just not let T4 run so that T6 finishes and we can go back to T3 because T3 has a higher priority than T4. But with this strict priority, we're going to run T4 and delay running T3 unjustly. Now, I ended up telling you what priority inversion is, but if you didn't get it here, don't worry, we'll come back to it with more details and more diagrams when we talk about real-time systems. Okay, now let's talk about fairness. This is strict fixed priority scheduling is absolutely not fair, right? Especially for low priority. This is a real example, I believe, in Multics, which is one of the earliest systems, if I'm not mistaken, at MIT. If I'm not mistaken, I don't know. This is on top of my head. They shut the system down at some point, and they found a task that was sitting in the queue for 10 years. So there was a 10-year-old task that was submitted 10 years ago and it never got to run. So this is possible, right? If you have a strict priority and you have this really low priority task, and every task that comes to your system is higher priority, you might end up not running that task ever. One approach is to divide the time that you put on running tasks in each one of these queues between the queues, right? So you might say, this is like the priority 0 tasks and priority 1's tasks, and then priority 2 tasks, and so on and so forth. You might want to say, I'm going to spend 80% of my time running high priority tasks, then 15% of my time running medium priority tasks, and then 5% of my time running low priority tasks. So in this example, let's say this is high, this is medium, and this is low, and you might divide your time between these queues so that your low priority tasks don't get starved. So at least they get to run 5% of the time. So this is one approach. Another approach that you could use is to kind of, if like a task is in low priority for a long time, maybe increase its priority to give it more priority. Or if you have a task running in high priority for a long time, decrease its priority, so that you give chances to others. So this one is kind of like you're changing the priority that is set by the user, but this is also possible. Okay, let's stop here. I'm out of time. Yeah, so this last point, let me make this point and then we end here. Usually fairness is achieved by hurting the average response time, right? So if you want fairness, you end up kind of hurting the average response time, usually. Like, for example, in the case of round robin, we ended up, having fairness because we ended up finishing all the tasks at the end. So we were fair between those tasks, but average response time hurt. Okay, so with that, let's end this section here. I was hoping to finish it, didn't happen. Discard. Let me just see where we are. So hopefully we can finish it up next time and move on to multiprocessor scheduling. Okay, thank you for sticking around. And take care and be safe. Talk to you on Tuesday. Bye-bye.